All right, so make sure you have your PowerPoints out, and because I'll hit the high notes, and you can make notes on them and everything. And this section 2.1 is actually a new one to the book. The book is in the 3rd edition now. It's called The Lords of Data. So I don't know if I agree with that title, but that's the title that was given. So whenever we study data, of course we want to use the scientific method. That's used a lot. I know you probably have taken some class where that has been introduced to you. The scientific method, though, it says it gives you 4 steps there. Gather information about the phenomenon being studied. On the basis of the data, formulate a preliminary generalization or hypothesis. Collect further data to test the hypothesis. If the data and other subsequent experiments support the hypothesis, it becomes a law. So usually we learn about the scientific method in high school, like a high school biology or chemistry class or something like that. And in a way, I guess, what we do in statistics, our end game in this class is to get to hypothesis testing. So once we've come up with that hypothesis, then how do we test that hypothesis? And in order to do that, we have to have a set of data to test our hypothesis. So in a way, we're using the scientific method, something like that. There are a lot of problems that we can run into, though, when you're collecting data. And some of those problems we have no control over. You can see there on the first page, bottom left, confounding variables, right, of your PowerPoint. It says confounding variables are extra variables that are not accounted for during experimentation and can cause results to become skewed. Okay, so they're variables that you may not be able to account for in your study. Like let's say we were doing a study on some vegetables that we were growing. Okay, and we wanted to know, if we use this kind of soil, if we use this kind of fertilizer, do our vegetables grow better? Or if we don't use it, do our vegetables grow better? And we planned, we got our plots, we went out there, we plowed our ground, we know where we're going to put all our vegetables, we got all our fertilizer, and so we got everything, we planted, and then it didn't rain for 2 months. We were unable to really provide enough water. Well, we can't really control that it didn't rain for 2 months. That's a variable that we probably should have accounted for, but we can't control that. So that would be maybe a confounding variable that would skew our results. Anything like that, though, if you're doing a study, anything. Let's say that we were doing another study, and in this study we were going to call, those telemarketers that we get all those calls. Anybody get calls from Waynesboro, Mississippi? Because I know I do. I get a lot of calls for some reason from Waynesboro, Mississippi. And usually whenever I answer, it's either a telemarketer or it's someone that just hangs up. I really think they're recording my voice so they can use it to do stuff, to maybe get into my bank account. I don't know. I'm paranoid. But anyway, let's say we were doing some kind of study and we were calling people, and let's say that we had to conduct our study. We wanted to see within 4 hours how many people actually answer the phone number that we call. And let's say that we only had 4 hours and we were going good for 2 hours, and then for some reason or another our phone service went out and we were only able to call people for 2 hours. I know it's hard to believe, but phone services, at least in the past, they used to go out a lot before modern technology. But that's something that we really can't control. Maybe we could go get another phone or something, but maybe we're in an area where we can't go get another phone. So little things like that, those are confounding variables. They're not accounted for. Like, we didn't think we were going to lose service. We didn't think that it wasn't going to rain for 2 months. I mean, it's been raining every couple days here. We've gotten some rain. We didn't believe it was not going to rain for 2 months if it's been raining normally. If we were dealing with those crops. So those are little things that can affect our outcomes. The next thing listed on your PowerPoint is the decision-making method. It says, and I'll read through these procedures for you. Clearly define the problem and any influential variables. Decide upon objectives and decision criteria for choosing a solution. Create alternative solutions. And then compare alternatives with the criteria established in the second step. All right, so just whenever we conduct our study and we're looking at the results, then the way that we interpret those results and the things that we do is very important. Maybe next time that I do that study with the vegetables, maybe I'll do it on a little smaller scale, and I'll do it in a greenhouse where I can control the weather. All right, so or maybe next time I do that survey, maybe I won't use a telephone. I'll just go stand outside by the cafeteria, and I'll see how many people I can get to respond to the questions that I need down there. So decision making, adapting, changing, figuring out if our results are valid or if there are any confounding variables that may have affected our results. The last part of that decision-making method, I didn't say. Number 4 says implement the chosen alternative and then check the results to make sure the desired results are achieved. Okay, so probably be a little easier to answer 3 or 4 questions down by the cafeteria than it would be if I was trying to call you on your cell phone. Who knows? Maybe you're in class and you're not going to answer. Or maybe you're like me, and if you don't recognize a number, you just don't answer the phone. I don't know that that's always the best option, but that's what I do a lot of times if it's on my cell phone. All right, so how do we actually collect the data? Collecting data. All right, so there are 2 ways to obtain data: observational and controlled. And those are both different types of experiments. So observational data. Just like it sounds. We're going to observe. Maybe I want to know how many students have their ID on as they walk past me when I'm standing down by the cafeteria. They have it visible. So observation, that would be like an observational experiment. I don't know if that makes sense, but let's see if there are any other examples here. All right, your book says the data collection method is related to the nature of the problem to be solved and the ethical and practical constraints of collecting data in some environment. There are many instances in which controlled experiments that will produce particularly appropriate data are not practical or would be unethical. For example, medical researchers cannot randomly pluck an infant's liver in order to experiment with a new artificial one. So, that would be ethical, right? It says a high school physics teacher wants to determine if there is any benefit or beneficial effect of studying calculus before taking physics. He obtains the records of his physics students and compares the groups of students that have calculus who are taking it concurrently with those who have not. The average physics grades for those having had calculus is a great deal higher than those who had not. The conclusion reached from the data is the study of calculus improves one's understanding of physics. So it's important how we collect data. It's important that we're always ethical when collecting data, and we don't try to trick people when we are collecting data. The way that you ask questions in surveys, we'll go over that. You can load questions so that you maybe get a certain response. There's a lot of tricky things that go on in the world, especially when you look at statistics. There's a lot of ways to trick people into thinking that something is what it's not. We'll go over some of those ways that people in the world constantly try to trick people and do trick people into thinking that something is that it's not. We'll go over that eventually. But it's very, very sad that there are groups out there that have a certain agenda or certain belief, and that they do trick us all the time, believe it or not. And I'm not trying to be paranoid, even though I am a little paranoid. That happens every day. All right, so in controlled experiments, let's see. Well, before I go through that, let's see what a response variable measures the outcome of interest in a study. I mean, that just kind of makes sense. That's just like a variable in a study, something that you're trying to measure. And explanatory variable, this is on the next page, causes or explains changes in a response variable. So ideally in controlled experiments, you're going to have two groups, right? You're going to have a control group, and you're going to have an experimental group. So we're going to have two groups. One of the groups we're going to do something to, hopefully knowingly. They'll know that we're doing it to them. And then the other group, they may think we're doing it to them, maybe not. Depends on what kind of study we're doing. And then we compare the two so that we can tell if whatever we did to the control group or the experimental group actually gave a different result. For example, if you're testing, maybe you want to test some new type of diabetic medication. Well, we're going to compare the old diabetic medication, all the results that we got from it, maybe with new patients who are taking the medication. So you have to have a group that maybe has been doing something this long time, and then another group that you do something else to, and then you can compare the results. And whenever we apply something to a group, maybe that new drug that we're giving them to cure diabetes, hopefully one day, right? We're giving them this new drug to cure diabetes. Well, whatever drug we're giving them, that's called a treatment to that group. Now, your PowerPoint goes through another example of like a control group and an experimental group. And let's just read through it real quick. It says, suppose a new species of tomato has been genetically engineered to increase yields. How can we measure whether the new species produces higher yields? It says the solution will be, in this experimental design, the plots of tomatoes will be divided into two groups. One that contains the new species and another that contains the unaltered variety. The plots containing the genetically engineered variety will be the treatment group. Okay, that something's been done to it, so that's our treatment group. And the plots containing the standard variety will be the control group. If the experiment is properly performed, any change in the response variable or yield can be attributed to the explanatory variable genetic engineering and not to other variables that are controlled. Variables like rainfall, amount of sunshine, and types of soil can affect the yield of tomatoes. These variables must be controlled in the experiment, so the difference in yields between the plots can be attributed to just the genetically engineered species. All right, and then it goes through, a way of doing that. It shows them making these little plots, or at least it's a figure that has plots on it, and it says rainfall is measured and supplemented with irrigation. See, that's what I needed with my experiment earlier. I needed irrigation. I should have thought of that. To assure that each plot has the same amount of rain. By controlling for these variables in this manner, we can say that any differences noted in the yield between the genetically engineered variety and the unaltered variety is due to genetic improvements. They go through another example about, does an SAT preparation course improve performance on the SAT? Now, ACT scores, everybody thinks they're the end all be all now, and there are a lot of ACT prep classes out there. Do they work? Well, what we would need to do is we would need to maybe record everybody's score before they took the prep class, and then have everybody score after they took the prep class. Then we'd be able to see if the prep class worked that everybody was taking. Does anybody know what a placebo is? You heard of a placebo? Yeah, the placebo effect. That's another definition in this section. A placebo is a fake treatment that has the potential to cause a response. So believe it or not, placebos do have an effect, or they can have an effect. Another type of study is listed in your book, a double-blind study. It says double-blind studies are used to counteract the placebo effect. In a double-blind study, the subjects are not told whether they are members of the treatment group or the control group. The evaluators, the persons that measure the response variable, are not told whether their subjects are members of the control or experimental group. All right, so then whenever you get all your results, you find out who was part of the control group and the experimental group, and you can limit that placebo effect. And bias. Bias is the tendency to overestimate or underestimate the value of a certain population parameter. At least in statistics it is. Let's see, here's a double-blind study. It says Until recently, ulcers in the upper intestine were a rather common illness. A new treatment for ulcers was proposed. This treatment involved gastric freezing and required the patient to swallow a deflated balloon with tubes attached. A refrigerated solution was then pumped through the balloon for an hour. The idea behind this therapy was to cool the stomach wall, reduce the amount of acid produced, initially. At first, the results looked promising and the treatment was used for several years. However, none of the initial studies were double-blind. In the double-blind study, half the patients were given the procedure and the other half were given a placebo treatment, which included swallowing the balloon, but no cooling solution was injected into the balloon. In the double-blind study, patients had the placebo treatment actually did better than the ones that had the real treatment. So gastric freezing was eventually abandoned as a treatment for upper intestinal ulcers. So that's pretty interesting there. Observational studies, it says, come about by measuring what is. If you're trading stocks, the market data you receive is observational. It's simply what's happening at the marketplace at a time. Census data is observational. More examples would be stock, commodity bonds, option, current market data, almost all federal government data, virtually all local and state government data, and sports data, all observational. One second. Another way to collect data, and I think I kind of talked about this, or I've mentioned it from time to time, surveys. So surveys is a good way to collect data. Of course, with surveys, it's important. Who are you polling? You know, who are you sending the surveys to? I don't know if I've seen them lately, but I know that some restaurants and places that you go and eat have little survey cards a lot of times. They used to be, before technology is what it is today. If you went down and if you sat down and ate a hamburger at McDonald's or Wendy's or wherever, there was a little survey card. Well, what's the problem with those survey cards? More than likely, you're not going to respond to a survey card unless you have something negative to say, right? If you go in and it takes you 30 minutes to get your hamburger, or like us, we were smart, me and my wife and my daughter, and we decided it was Christmas night. We decided to go to McDonald's in Cleveland, Mississippi. And the drive-through was out to the road, so we'll go inside. Well, 45 minutes later, we got our food. So, and the whole, around 30 minutes, I'm thinking, man, I'm gonna get online and I'm gonna complain to somebody. I didn't though. I was like, we're the dumb ones. We went in there on Christmas, Christmas night, or maybe it was Christmas Eve. It was one of the two. But yeah, so surveys are good. If surveys are optional, though, you need to be prepared for the results that you're going to get. Your book says steps to consider when conducting a survey. I'm not going to ask you these questions. Again, these first couple sections are all just terminology. But it says have specific goals, consider alternatives for collecting data, select samples to represent the population, match the question wording to the concepts being measured, pre-test questionnaires, construct quality checks, use statistical analysis and reporting techniques, disclose all methods used to conduct the survey. I read somewhere, and it was in one of the statistics books that I've used before. It said that there was a study that was presented by a company that said that chocolate, I believe it was something like chocolate extended life expectancy, or chocolate, it was something to that effect, had some positive effect. And if you dig deeper, though, you could find out that the study was funded by Hershey. So, yeah, of course Hershey is going to want to put out a study that chocolate has a positive effect, even though I think it is kind of positive at times, right? You get that sugar rush and feel good. But what about all the bad effects that if you eat too much chocolate, maybe a little chocolate is good for you. But anyway, that study, you have to be very skeptical when you see studies come out. If it doesn't sound right, I would always try to look for sources. Look for who funded the study. Okay? All right. In 2.1, a lot of terms, a lot of terminology. We'll actually be able to do a little more in the next section. All right, data classification. A lot of different ways to classify data. All right, two types of data are discrete data and continuous data. All right, so discrete data, observations that have gaps. So, for example, if I had a couple of chickens that laid eggs, and I wanted to collect data on how many eggs my chickens lay each day. Well, I'd go out there on Monday and collect some eggs, go out there on Tuesday and collect some eggs, and I would have whole number answers, right? I would never come inside with 3.5 eggs. Right, I wouldn't. Maybe I'd come in with 3 eggs on one day, 5 eggs the next day. That type of data, that is discrete data. It is countable. All right, there are gaps. One day I may come in with 2 eggs, the next day I may come in with 6 eggs. There are gaps between my answers. All right. Continuous data is data that can take on any value in a given interval. So let's say that, think about your height as you grow. One day you're 5'2", and then maybe a month later you're 5'3". Well, you just didn't overnight, you didn't go from 5'2" to 5'3", right? You gradually grew that inch, and you, at some particular time, you were every measurement between 5'2" and 5'3", right? So there's no gap there. Data like that, where there are no gaps or no holes, that's continuous. All right. Now, the next thing that we're going to go over the different levels of measurement. This is probably, I'd say, in statistics or in research, this is one of the things that one of the first things students have trouble with. All right, the levels of measurement. And I'm going to refer to a couple of the other two handouts that I gave you when we talk about these levels of measurement. So we have 4 levels of measurement. All right, 4 levels of measurement. We have the nominal level, and I'm going to skip a little space in between these. Ordinal level. The interval level. And the ratio level. All right, these, in a way, these different levels of data are from least complex to most complex. Okay, the way that they're written down right now, the nominal, ordinal, interval, and ratio. I don't know why I put level on the end of that, even though they're all nominal level, ordinal level, interval level, ratio level. All right, so in the nominal level, that would be a set of data that you have categories, okay? And those categories really can't be ranked. So if you look at one of the sheets that I gave you, look at those 2 sheets. This was a Microsoft form that I gave to my online statistics class previously. And I got them to answer a few questions. So if you look on the page and at the very top where it says, what color are your eyes? That would be nominal. That data is at the nominal level. Really can't order that. I mean, I guess if we wanted to consider order as alphabetizing, we could. But other than kind of grouping them together a little bit, we can't really order that. You know, I can't say something like brown minus green equals blue. That doesn't make any sense. Okay? So that data could be considered at the nominal level. Also, look at the next one. How do you identify yourself politically? All right, the 3 choices were independent, Democrat, or Republican. All right, and so there's all the answers. Now, how can those be ranked? Now, in some people's minds, maybe they could rank them. You know, if they have strong feelings about one political party or another. But, you know, Republican minus Democrat doesn't equal independent. That's not the way it works. Okay? So that's also at the nominal level. So that's almost like the simplest level of measurement. So that's nominal. Now the ordinal level can have the same properties as nominal, except it also can be ranked. All right, you can rank the data. For example, let me show you. This is something out of your textbook. If I ask you this question and we all had tasted Frosty Pops, then I could take that data and I could rank it from very bad to very good, or very good to very bad, right? I could rank that data. I could order it in some way, and it would have meaning. All right. However, I can't add the data. Like, let's say that the first person that I looked at gave it a 1, and the second person gave it a 4. Well, 1 plus 4 is 5, so does that mean that if I put those two people together, that's a very good rating? No, it's not. So adding the data doesn't make any sense, or subtracting the data really doesn't make any sense. But ordering the data would make sense. We could understand that if we had a lot of 1s, if I was to give this question to 28 people in the classroom, and I saw that the first 20 answers after ranked were 1, then it's probably not a very good treat or cereal or whatever that is, that Frosty Pops. Maybe that's maybe it's a popsicle. I don't know. That's the ordinal level. So we had the nominal level, labels that really can't be ordered. You may be able to sort them, but you can't really order them. Then we have the ordinal level. All right, can be labels, can be numbers, can be sorted. The next level we're going to look at is the interval level. So if you can take sums or differences and it's meaningful, and really your book just says arithmetic differences. If the arithmetic difference is meaningful, then you are on the interval level of measurement. All right, there's one other property that interval data has. All right, your book says interval data also has another interesting property, an arbitrary zero value. Arbitrary zero value. What do you think that means? In other words, a zero value that was defined as such for no particular reason. All right. For example, a temperature of 0 degrees on Celsius or Fahrenheit scales does not mean that there's no temperature. If I say there's no temperature outside, then something's wrong. And that doesn't mean there's a temperature of 0. It's a difference, right? Your book says that doesn't mean there's no kinetic energy. All right? So, data like temperature So I could write down the temperature every day in Mississippi's not a real good state to talk about interval data because usually we don't get temperatures below 0 or 0. We have before, but maybe just once or twice in my lifetime. But if we were in a northern state, we would have positive temperatures. Maybe some days it'd be 0. We'd have negative temperatures. So that type of data is interval data. Because if I take the temperature from Monday and I take the temperature from Wednesday, I could subtract and get a meaningful answer. Maybe Monday was 15 degrees colder than Wednesday. It would make sense. Maybe I want to know the difference in the days of the year. I take the temperature from every Monday. And I want to know the difference in the first Monday in November and the first Monday in June. Well, I can take that, I can subtract. All right. Temperatures also have that arbitrary 0. So that would be at the interval level. All right. The last level is the ratio level. So it has all the same properties as the interval level, but it has a meaningful. So you can take those differences, but it has a meaningful 0 value. All right, so if you look at those two sheets that I gave you, the ones that had the questions on them, if someone, let's say on the question, how many college hours are you taking this semester? And it's not, this answer is not down there, but if someone put 0 hours, then that would mean they're not taking any hours, right? That's meaningful. I can still sort that data. I could still say, hey, you're taking 21 hours and I'm taking 16 hours, 21 minus 16, so you're taking 5 more hours than me. So that makes sense. That's I guess, has value in that. But if I'm taking 0 hours and you're taking 17 hours, then 0 has a meaning. Same for the GPA. You see how those GPAs listed? If your GPA is 0.0, that means you have failed everything, right? With an F. Luckily, none of those were down there. So that would also be ratio. What about how old are you? If you're 0 years old, I guess that's how old you are before you're born. I don't know. I guess the time that we usually count is just after you have been delivered. But 0 years old, you can't be -1 years old, right? So a meaningful 0 value. If I was in 10 years to call everybody in here and say, what is your salary? And I convinced you to tell me. And I put it all in a spreadsheet. If your salary is $0 because you're not working, then that has meaning. Hopefully that won't happen. Everybody in here have a lot of money 10 years from now. Can we think of some other arbitrary value other than temperature? Because it's that's always the example that's given, is temperature, the arbitrary 0. One that I had thought about is if we start talking about like calendars, the year 0. Well, our calendars that we use are before Christ and after Christ, right? What about those years in between? That's not years 1, 2, and 3. Is it? Think about it. All right, so that's the 4 levels of measurement. We have nominal, ordinal, interval, ratio. And they go like from least complex to most complex. And the main difference between interval and ratio is that interval, if it's 0, it's not the 0 that we think about as nothing. All right? But with ratio, it has a meaningful 0. 0 means 0. All right. Now, 2 ways to categorize data. We can categorize data as qualitative or quantitative. All right, so qualitative data, that's going to be on the nominal or ordinal scale. So if it's something that's labels, like the color of your eyes, if I had a set of data on the color of everyone's eyes in here, that would be on the qualitative, that would be qualitative data. Okay. Even numbers sometimes could be qualitative. What about the numbers on the back of jerseys, sports jerseys? You know, number 11, that's a label, right? That's, hey, number 11, you know, that's what bad fans call out sports people, you know, talk about people. Hey, number 11, you're not very good or something like that. Well, those are labels. So that, even those numbers can be labels sometimes. Don't do that, though. Don't make fun of people. Be nice. Always be nice. And then, of course, quantitative. Quantitative. That would be data that's on the interval or ratio scale. So all that data that has meaningful differences, you know, you can take one and subtract one from the other and have some kind of difference between the two. Whether or not it has a natural 0 starting point, that is quantitative. So I think quantity, quantitative, quality, qualitative, that's the way that I kind of keep that straight. But just remember, qualitative is more labels and things like that. All right, the last thing we're going to go over today is time series data and cross-sectional data. So time series data, your book says time series data originates as measurements usually taken from some process over equally spaced intervals of time. And then one of the examples they give is, it says, a batting average represents the percentage of time a player gets on base as a result of a hit. In Major League Baseball, the better players have batting averages between .300 and .400, which means they get on base as a result of a hit between 30 and 40% of the time. The following table is a list of batting average champions of the American League since 1970. And then they give, that's really small, I apologize, I know you can't read that. That is also in the textbook. Let me see if I can pull it up, even though you may not be interested in it. It is a little interesting to see from year to year. See if I can find it. Here's some batting averages right here. This was the American League batting champion from 1970 to 2017. So you can see pretty much between what we call 300 and 400 is .300 and .400. You don't see anybody at .400. You see somebody kind of close right there, George Brett. 39% of the time he got on base with a hit. Of course, that doesn't count a walk. That doesn't count if you hit the ball and there's an error. That doesn't count. If somebody's on first and you hit the ball and they get the person on second out, but you get to first, that still doesn't count as a hit. So, very hard to hit a baseball, apparently. All right, but that's data over some given amount of time. And then, of course, there are all kinds of ways to present that data. The data can be presented like this, right, in a table form. If we wanted a better idea of how the data has changed over time, would be better to present it in some other way. Like maybe, do you remember, have you ever seen like stock market increases and decreases, and they have the lines that go up and down, or you want it to go up if you're looking at a certain stock, but if you're looking at it over time, so the day it may have went up and then it may have been way down, and here's where Apple stock is right now. It's went down a lot here lately. But stock market data, it's usually measured over time, and it's usually presented to us over time. Sometimes that can be misleading, but that is time series data. Cross-sectional data, that's the other type of data. There's a lot of different examples of time series data that your book goes through and that the PowerPoint goes through. And then it doesn't give much on cross-sectional data on the PowerPoint. The book does. But your PowerPoint says that cross-sectional data are measurements created at approximately the same time. So, for example, let's see, I saw a good example right here. So, at the same time, so let's see what year this is that's given. In 2015, right around the same time, this data was collected. Life expectancy at birth in 2015 was collected in these countries. So all around the same time they got this data. That's cross-sectional. So you can see the places that you do not want to live, more than likely. then you can see the places where you may want to live, right? You can see those. Well, I mean, this was all done right around the same time. So it's like they took a cross section and analyzed this one piece of data, this type of, or I guess the life expectancy in all these different regions. So you see the difference? Time series is going to be over some amount of time. Cross-sectional is going to be it all, you're looking at it at once. So whenever you look at, usually, if I want to look at ACT scores for 2018 in all 50 states, that would be cross-sectional, right? If I want to look at ACT scores in the past 10 years for the state of Mississippi and how it's progressed or regressed, I guess, or increased or decreased, then that would be time series data. Does that make sense? Two different types of data.